Next, compressor. So, ito yung isa sa parts. Unahin natin yung compressor. Meron tayong mga types of compressor. So, the most common compressor used in chillers are reciprocating, rotary screw, centrifugal, and scroll compressor. Chiller units, meron siya evaporator and condenser. Yung evaporator, yun ang pagpuproduce ng chilled water. Malamig na tubig na papasok sa aircon na ang coil hindi refrigerant kundi chilled water ang ginagamit. Okay? So, kaya tayo tinatawag na chiller. So, each application prefers one or another due to size, noise, efficiency, and pressure issue. Compressors are often described as being either open, hermetic, or semi-hermetic. To describe how the compressor and or motor is situated in relation to the refrigerant being compressed. Yan. Yan ang description niya. Hermetic, semi-hermetic. Meron siyang enclosed, enclosed. So this is yan. Variation of motor compressor types can lead to the following configurations. Ito yung hermetic motor, hermetic compressor, hermetic motor, semi-hermetic compressor, open motor, built limit or closed coupled, hermetic compressor, open motor, built limit or closed coupled, semi-hermetic compressor. Yung hermetic ata yung enclosed, ito naman semi-enclosed, ito naman open. Ito lang. So, unahin natin yung reciprocating compressors. Common na sa inyo ito, di ba? Reciprocating, ito nag-reciprocate. So, this is a piston style, positive displacement compressor. Yeah. So, di ko na-discuss. Yung performance. Two of the most important performance characteristics of a compressor are its refrigerating capacity in its power requirement. Ilang tons? Kailang yung kilowatt. These characteristic of a compressor operating at constant speed are controlled largely by suction in discharge pressure. So, means controlling device ka dyan. Yan ang setting mo. So, next is the volumetric efficiency. So, na-encounter nyo ito maraming beses. Diba? So, volumetric efficiency are the basis for predicting performance of reciprocating compressor. So, two types of volumetric efficiencies will be considered, the actual and the clearance. So, the actual volumetric efficiency (SOVA) is defined by volume flow rate entering the compressor, entry, cubic meter per second, or CFM, divided by the displacement rate of compressor, where the displacement rate is the volume swept through by the piston intersection. So, clearance volumetric efficiency also depends on the expansion of gas trap and the clearance volume. Ito yung clearance mo. As in figure 8. The maximum volume in the cylinder, which occurs when the piston is at one end of its stroke, is B3. The minimum volume or the clearance volume is BC. So, which occurs at the other end of the piston stroke. The discharge pressure is piston P. Yan. Kasi i-compress mo, so ibig sabihin limited in volume sa clearance niya. So that means dito yung maximum pressure. Discharge pressure. Okay. The volume of the gas flow into the cylinder will be P sub 3 minus P sub 1. So, the clearance. And the clearance volumetric efficiency is N sub BC for this case is B sub 3 minus B sub 1 divided by B sub 3 minus B sub C times 100. Kasi di sa umabot. Diba? Ang clearance mo. Ito operating mo ito lang. So, dito lang P sub 2, P sub 1. Ito naman is yung discharge pressure. So, when the suction pressure is P2. So the intake portion of the stock is reduced to P3 minus P2. The clearance volumetric efficiency can be expressed in another way. This stated in figure 8 using P1 as the suction pressure. The present clearance M, which is the constant for a given compressor, is defined as M is equal to BC over BC3 minus BC. Percentage ng displacement. Diba yung BC? Ito yung operation mo. Ayan. Wait, ayusin natin. Adding BC minus BC to the numerator of the expression for N sub BC gives masiro din yan, walang problema. So B3 minus BC plus BC minus B1 over B3 minus BC. So mga operation to ang papakita mo kung paano naging so times 100 is equal to this one is 1, so magiging 100 lang plus BC minus B1 over B3 minus B1 times 100. So magiging 100 minus, so ito the same. So yan. Ito na. Natin. BC over BT minus BC times B1 minus BC minus 1 times 100. Tama. Ito pala binaligtad. So yan. Para maging pumasok to. Okay. Therefore, the volumetric efficiency is 100 minus clearance volumetric efficiency is 100 minus M times B sub 1 over B sub C minus 1. If an isentropic expansion is assumed between BC and B1, so B sub 1 over BC is equal to B suction over B discharge, where B suction is a specific volume of vapor entering compressor and B discharge is the specific volume of vapor after isentropic compression. So values of a specific volumes are available from pressure enthalpy diagram of the refrigerant or from table of properties of separated vapor. So substituting equation 6 dito, so equation 7 mo, N sub BC clearance efficiency is 100 minus M times B suction divided by B discharge minus 1. Yan. Okay. So yan yung volumetric efficiency mo. Clearance. This is the actual. Ito yung volumetric clearance volumetric efficiency. So application later na. Example na lang. So performance of the itong clearance diba ito ratio niya volume with entering the compressor. So ang clearance mas maliit. Yan. Figure 9 shows the effect of evaporating temperature on the clearance volumetric efficiency. So yan, ginap niya. So the mass rate of flow controls the capacity and power requirement more directly than the volume rate of flow. So the mass rate of flow, W kilogram per second through a compressor is proportional to the displacement rate in liters per second, and the volumetric efficiency and the volumetric efficiency is inversely proportional to the specific volume of gas entering the compressor. In equation form, W is equal to displacement times N sub BC over 100 over the suction. Example number 3. An ammonia compressor of 5% clearance volume and a displacement rate of 80 liters per second and pumps against a condensing temperature of 40 C. For the two different evaporating temperature of negative 10 and 10 C, compute the refrigerant flow rate assuming that the ERAS volumetric efficiency applies. The given ammonia compressor, 5% clearance, displacement rate 80 liters per second, condensing temperature is 40 C, evaporating temperatures are negative 10 and 10 C. Required refrigerant flow rate. Solution from equation 8, W is equal to displacement rate times N sub BC over 100 times the suction specific volume. Yan ang formula. So A, at negative 10 C, table 80, so current Jones ammonia, S sub 1 is 5.7550 kilojoule per kilogram. So, kasi gagamitin mo, wala kang gamitin na dito, di ba? P. So, kailangan makuha, mo ilista yung into P kasi mag-proportion into P tayo. S1 is equal to 5.75 per kilogram and the suction specific volume 417.477 liters per kilogram. And on 40C, constant entropy, figure A1, so this is the chart. The B discharge is 112.5 liters per kilogram. So, okay na ito. Hindi na tayo decimal places kasi block to. Diagram ang bibigyan mo. Okay? So, mag-point ka na lang. One decimal na. M is 5%. The equation 5 and equation 6, S of B is equal to 100 minus M times P suction of the B discharge minus 1. 100 minus 5 times 417.477 over 112.5 minus 1 becomes 86.445%. This is the volumetric efficiency. So, meron ka na niyan, meron ka nito. Displacement rate given as 80. So, W is equal to displacement rate times N sub BC over 100 divided by the suction of specific volume or 80 liters per second times 86.445 over 100 divided by 417.477 is 0.166 kilogram per second. This is for negative 10 C. At 10 degrees C, table 80, so S1 is equal to 5.4924 kilojoule per kilogram. Also, suction specific volume is 305.22 liters per kilogram. And at 46% entropy, discharge specific volume is 90 liters per kilogram. Equation 5 and equation 6 gives N sub B is equal to 100 minus M times V suction divided by V discharge minus 1. Substitute values which give 100 minus 5 times 205.22 over 95 minus 1 equals 24.199%. W is equal to displacement rate times N sub BC over 100 over V suction is equal to 80 liters per second times 94.199 over 100 over 205.22 or 0.367 kilogram per second. Answer for 10 degrees C. Okay. Power requirement. So the power required by the ideal compressor is the product of the mass rate of flow and the increase in enthalpy during the isotropic compressor. Same thing to the power P is W times delta X. This is in kilowatts. If the rate of flow is kilogram per second and the change of enthalpy as a topic work of compression is in kilojoule per kilogram. So, pag actual, process dito sa topic, diba? So, dito lang, discussion na ito dito. So, figure 10 shows the variation in delta X as evaporator temperature changes. Ito. Evaporator temperature, tama, value. So, ang power mo, ito, meron siyang peak. This is the power and ito naman work of compression in kilojoule per kilogram. So, value mo dito, at different evaporator temperature, mag-iiba yung flow rate mo sa computer. Tayo dito. So, ito magiging performance curve mo. Work of compression and power required by an ideal compressor refrigerant 22, 4.5% clearance, 50 liters per second displacement rate, and 35 degrees condensate temperature. So, at different evaporative temperature, mapabago yung mass flow rate mo. So, ito magiging result ng power mo. So ito naman, sa work of compression, yung delta S na ito. So, check nyo, isa-isa. Kung saan yung ano yung proof nito, check nyo isa-isa. Yun yung magiging ano ng proof nyo. So this is the 35C. Pag condensing mo, nag-equal sa evaporating, so magiging 0 yung support mo. The value of delta Si is at low of evaporating temperature to the side and drops to 0 when the suction pressure equals to, wait, so ito, so yung kaninang discuss ko pala yung nakalaki. Ito in words. The value of delta Si is large at low evaporating temperature. Ito dito, so laki, di ba? 25, 20, malaki, hanggang maging 0 when the suction pressure equals the discharge pressure or the evaporative temperature equals the condensing temperature. So, pinagit ko na rin kanina. Okay, nauna yun bago sa slide. So, the curve of power requirement in figure 10 therefore shows a 0 value at 2 points. So, nakato. Between the two extremes, the power requirement is peak. Yeah. 0. Hanapin mo yung peak power. Next, the refrigerating capacity. The refrigerating capacity is Q is equal to W times S1 minus S4 in kilowatts, where S1 and S4 are enthalpies in kilojoule per kilogram of refrigerant heating during the evaporator, respectively. The refrigerating effect, S1 minus S4, decreases, ito yan, slightly with an increase in suction pressure. So, the refrigerating effect. When multiplied by the mass flow rate, ito na yung nalang niya. Okay. Slightly. So, slight lang nakita dito. Provided that the enthalpy entering the expansion band remains constant. Refrigerating effect and capacity of ideal compressor, refrigerant 22, 4.5% kilos, 50 liters per second. Displacement is 35, 20, 30, 35. Yeah. Condensing temperature, 35 to. Yung point na yan. Ito, pataas pa to. Okay na yan. Ibig sabihin ko figure. So, the increase is due to the slightly higher enthalpy of saturated vapor at higher evaporating temperature. Figure 11 also shows the refrigeration capacity calculated with equation 10. The capacity is 0 at the point where the mass rate of flow is 0 kasi multiplier mo yun. So the refrigerating capacity is doubled, for example, by increasing the evaporating temperature from 0 to 20. C. Yeah. Ito, multiply ito. Kasi nagbabago yung mass flow rate mo. Depende sa kung nagbago rin yung evaporating temperature. So yan ang relationship ng evaporating temperature and refrigerating capacity. So ikita nyo itong mga graph sa catalog mga compressor mo. Compressor, pag isang system na siya, nakikita mo to. Okay? Yung performance, para data to, performance data. Nakikita mo to. Sa mga factorer, meron sila niya. Okay? Ngayon, meron ng mga software, pero hindi yan reliable na software doon kasi may mga minsan may bayad. Kung nakuha mo na, model lang nila ang kailangan gawin. Mag-select ka pa. pag-aaralan mo pa yung paano mag-import. So, mas maganda pa rin yung mga nakatalog kasi mas marami kang papipili. Next, the coefficient of performance in volume flow rate per kilowatt of refrigeration. So, the coefficient of performance can be derived from the refrigerating capacity in figure 11 and the power from figure 10. The result displayed in figure 12 shows a progressive increase at the evaporating temperature increases. Ito yung figure 12. This is the COP of coefficient of performance in volume flow per kilowatt of refrigeration for ideal compressor. Refrigerant 22, 4.5%, 15 per second displacement, and 35 degrees condensing temperature. Ito, pwede mo ito kumuha na ganito ng manual. Kuha ka ng graph, ganyan din. Pag-iba na yung refrigerant. So, pwede kang gumawa nito, madali lang naman. So, pag-aralan mo lang yung sa isa. Isa-isa mo lang computer. So, Excel. Tapos, ipagtat mo na. Diba? Lang yan. Lahat naman yan may kukuha sa equation. So, the volume flow rate per unit refrigeration capacity is an indication of the physical size or speed of the compressor necessary to develop 1 kilowatt of refrigeration. A large volume flow must be pumped for a given capacity at low evaporating temperature. So, yan. Because of the high specific volume. Sabihin, mataas large volume flow at low evaporating temperature. Ito yung low side. Alam ko, mababa to. And COP, ito na labas na. Now, the effect of condensing temperature. So, may response yan. Kasi yung system mo, ibabalance mo. Meron ka ng performance ng evaporator, condenser, compressor. So, dito sa condenser lang, ibabalance mo siya. So, the response of a reciprocating compressor to changes in condensing temperature can be analyzed similarly to the evaporating temperature. So, figure 10 shows the clearance volumetric efficiency as calculated from equation 7 for a compressor with an evaporating temperature of negative 20 C. Negative 20 C evaporating temperature. Ito na tagdag. Diba? Yung basis niya. Ano yung value mo, design value mo dito kapag sa isa lahat ng curve na to. May mga value ka dito. So, makukuha mo na itong mga POP. Kung sa mag-select ka sa ano yung flyer, ng conclusion ng flyer, ng walang engineering data, may select mo doon is nominal. Okay? Paano pag pinano sa'yo, pinabusisi, point to point tama yung function. Ano ganito yung, kasi bawa nakalagay doon is 25 na 40C ang ginamit sa brochure, isa yung 35. So, kailangan mo pag-aralan yung sa 35. Pero yung 40, ginamit ko lang yung for reference lang. Para makakuha ka ng dimension or nominal nominal design lang yun. Pero pag pinabosisip mo na yung ito, yung tawag na simulation. Atin, simulation computer, parang glowing na. Pero ang totoo simulation, i-computein mo to isa-isa. At negative 60, negative 40, negative 20, 0, 20, isa-isa yung yan. Hindi yan connect that na lang sa safety. So, the volume flow rate per unit refrigeration, yan, tapos, okay. Effect of condensing, ito pala. As the condensing temperature increases, so nagbababa yung volumetric efficiency because the specific volume of the refrigerant of the compressor sucker remains constant. Only the volumetric efficiency affects the mass rate of flow, which shows a corresponding decrease as the condensing temperature decreases. Pababa. figure 14 shows a progressive decreaser. Condensing temperature, refrigerating capacity. So the refrigerating capacity is the product of the refrigerating effect and the mass rate of flow, both of which decrease with increasing condensing temperature. The result is that the refrigerating capacity drops rather rapidly on an increase in condensing temperature. Ginamit ko na dati yung pag-analyze ng AHU, tapos merong condenser, hiwa-hiwalay. Yung mga split type. Yung mga may piping, parang hindi sa package. Pag hindi sa package, hiwalay na. So, kailangan compatible yung mga performance. Kita mo, hindi yung pag select ko dito, iba yung balyon makukuha doon sa evaporator, iba dito. So, wala kang design. Yung analysis, lang. Kailangan natin analysis mo may reference point. So, pwede mo gamitin sa mga video. Diba? Magiging guide niya yan. So, the remaining important characteristic is the power. Yeah. Power of compression is per kilogram. Ito naman yung power multiplied ng storage, yung work of compression. So, the compressor power is the product of work of compression in kilogram per kilogram and the mass rate of flow. The work of compression in kilojoule per kilogram increases and the mass rate of flow decreases as the condensing temperature increases, so that the power increases to a peak and then begins to drop off. A trend similar to the project as a function of the evaporating temperature shown in figure 10. Actual volumetric efficiency. So ito kasing clearance volume efficiency prediction. The prediction of volumetric efficiency on the basis of the expansion of vapor in the clearance volume is a good start toward predicting the actual volumetric efficiency. Other factors that influence the volumetric efficiency are the pressure drop across the suction and discharge valve, leakage past the wing of the piston, and leakage back to the discharge and suction valve. Also, cylinder heating of suction gas reduces the volumetric efficiency, since immediately upon entering the cylinder, the gas is warmed and expanded. The specific volume of gas inside the cylinder is consequently higher than when entering the compressor, which is the position on which the volumetric efficiency is based. All the above mentioned factors result in a lower actual volumetric efficiency than that predicted by the expansion of clearance gas alone. Figure 16 shows the actual volumetric efficiency compared to with the clearance volumetric efficiency. So, figure 16, clearance in actual volumetric efficiency of a refrigerant 22 high-speed compressor. The clearance volume assumed for calculating the clearance volumetric efficiency is 4.5%. Metering discharge to suction pressure ratio. So, makuha mo yung clearance volume metric efficiency, yung may formula, ito yung walang formula, the actual selection siya. Diba? Pwede ka gamitin to. I-neglect mo muna itong refrigerant 22, 4.5, considering na same sa ibang refrigerant. So, pwede mo itong in the future magamit na compute mo clearance efficiency, hanapin mo yung nakatap dito, yun ang magiging estimate mo na actual. Okay? Yun ang ginagawa ng mga design. Hindi yun ang work na. Pag-select ng design, oh, balik to. Tanggalin to. Now, compression efficiency. The compression efficiency in percent is isentropic work of compression divided by actual work of compression times 110, where the work of compression are referred to the same suction and discharge pressure. The compression efficiency for open type reciprocating compression are usually in the range of 65 to 70%. Some of the processes that reduce the compression efficiency from its ideal value of 100% are friction of rubbing surfaces and pressure drop to bar. So, yeah. Okay? So, kung nag-size ka ng nakuha mo yung value of work, nakuha mo yung power, wag siya pili ka agad ng motor, wag. Kailangan tingnan mo kung ano yung efficiency. Okay? Kasi may ginagawa compute lang, kung theoretical, 100% pipili ng motor. So, hindi pwede yun. So, example number 4, the catalog for refrigerant 22 4-cylinder hermetic compressor operating at 29 revolution per second, a condensing temperature of 40 C and an evaporating temperature of 4 C, negative 4 C, shows a refrigeration capacity of 115 kilowatt. At these operating points, the motor, whose efficiency is 90%, draws 34.5 kilowatt. The bore of the cylinder is 87 mm and the piston stroke is 70 mm. The performance data are based on HC of some cooling of the liquid leaving the condenser. Compute A, the actual volumetric efficiency, and B, the compression efficiency. So given is refrigerant 22, E2.